The next section is about exponential growth, and it's really kind of an application of differential equations, and it's a special differential equation that works out to be the exponential growth equation. And you have worked with exponential growth in the past, so that shouldn't be new to you. The part that's new to you is seeing it as a differential equation. So in those exponential growth situations that you're familiar with, the rate of change is proportional to the amount that you have. So like bacterial growth is a great exponential growth situation. And if you have more bacteria, then you will have a faster growth rate because the more bacteria are going to be all of them reproducing, so that gives you a faster rate. Or radioactive decay, when you have more of the radioactive isotope, the decay rate is faster than when you have less of it, because that's how half-lives work. And in your bank account, if you have continuously compounding interest, if you have more money in your bank account, then your rate would be faster. Your growth rate is going to be faster when you have more. So this is that statement as an differential equation. So the rate of change of y with respect to time is proportional to the amount. The rate of change is directly proportional to the amount, is what those symbols mean. And so if we look at that, if we look at the rate of change is directly proportional to the amount, we can solve that because it's a differential equation. So we're going to go ahead and do that. And it's actually a nice separable differential equation. So the first thing we're going to do is separate out the variables. Oops. So we have dy divided by y equals k times dt. Hope that's okay. Once we've separated out the variables, then we can take the integral of both sides of the equation. The integral of 1 over y would be the natural log of the absolute value of y, and the integral of k dt would be k times t. And then we need to have a plus c. Whenever we integrate, we need to have a plus c. So remember, we want to solve for y now, so we're going to get rid of the natural log. We're going to raise both sides e to the. And then I'm going to do the next step. Still, absolute value of y is equal to e to the kt times e to the c. And the reason that's true is because of an exponent rule. A to the b times a to the c is equal to a to the b plus c. So there's an addition in the exponent. If we go backwards, we can turn that into a product. And now to get rid of the absolute value sign, we have y is equal to plus or minus e to the c times e to the kt. All right, so our steps again. First, we separated out the variables. Then we did the antiderivative. And then we're solving for y. And this step here, we made use of the exponent rule that allows us to change our exponents. Multiply instead of add exponents. And then we recognize that since e is a constant and c is a constant, then e to the c would be a constant. And if it's plus or minus e to the c, it's either positive e to the c or negative e to the c. So we're going to just give that a name, and it's a constant, but we're going to call it p instead of calling it c. And so we wind up with y is equal to p times e to the kt. And that looks a lot like an equation that you learned about in intermediate algebra class or advanced algebra class, which is y equals p e to the rt. So we just use the letter k because that's what we usually use for proportionality, but pect or pert are basically the same thing. So that's the proof of this next statement, but here's the statement. The law of exponential change, if y changes at a rate proportional to the amount, And if y equals p when t equals 0, then we have this too. We get the equation y equals p times e to the kt. And k is a growth constant if it's positive, and it's a decay constant if it's negative. So here's an example of exponential growth. At the beginning of the summer, the population of hornets in a hive is growing at a rate proportional to the population. So that tells us dy dt is equal to the population times k. So that immediately, that looks like our exponential growth situation. So we know that we could go through the whole process, or we could say, I don't need to go through this process every time. When I see this differential equation, I know that it's associated with this solution. And then we're going to make use of this information about May 1st. We're going to call May 1st t equals 0. And when t is equal to 0, we know that there are 10 hornets. So I'm going to fill that in. 10 is equal to p times e to the 0. E to the 0 is just 1, so that means that p is equal to 10. So now our equation is y equals 10 e to the kt. And I'm going to use this other information. 30 days later, there are 50 hornets. So t equals 30, y equals 50. And I'm going to use that to figure out what k is. So once I know the growth constant, then I can figure out how many days until the population reaches 100. So fill that in. 50 is equal to 10 times e to the 30k. And if I want to solve for k, I would divide by 10. And natural log both sides. And divide by 30. So k is equal to natural log of 5 divided by 30. So now we have the actual equation for these hornets, which we hope are not really murder hornets. We have y equals 10 e to the natural log of 30, natural log of 5, over 30 times t. And our question is, how many days after May 1st until the population reaches 100? And this is a situation when I want to encourage you to stop yourself from doing too much algebra and grab your calculator. We're going to try to figure out when this exponential equation is equal to 100. So this is a great situation for graphing and finding the intersection. So I'm going to go ahead and show you how to do that. We're going to grab our calculator. All right, so on my graphing calculator, I'm going to type my equation, 10 e to the, make sure you use the actual e button, not the letter e. Natural log of 5 divided by 30 times x. I'm missing a parentheses. How's that? Do you need parentheses around the 5 here? Ah, there we go. And my window is bad. And it makes sense that my window is bad. I'm going to change my window. So I'm going to go Menu, Window Zoom, Window Settings, and I'm going to say, well, I don't really care about any negative x's, but I'm going to change my x max. I don't know how many days it's going to be until my population is that big, so I'm going to make it 100, but I'll bet it's smaller than that. And then I need my y max to show me 100, so I'm going to make this 120 just to make sure I can see it. And then in order to figure out when the population is 100, I'm going to need to enter another equation. So I'm going to hit Tab so I can enter another equation, and then I'm going to graph 100. And it looks like I chose a pretty good window because I can see where they intersect on my screen. So I'm going to hit Menu, Analyze, Intersection, click to the left, click to the right, and it looks like it would be 42.9 days, but remember this is calculus, so we want to always be correct to 3 places to the right of the decimal. So if your settings are not set to float, make sure you change those. So 4.920 would be how many days it is. Wait, is that right? 42.920. All right. So I'm going to make a separate video for the next example, but there will be another video for this section.